started. Um, there should hopefully a few more people still coming in, but hopefully you had a good and a safe weekend. And the first announcement that we have is that we will have our first written quiz on Friday. Remember, I told you we're announcing those this semester, so both sections have the same amount of notice. The quiz will take place at the beginning of class, right when the bell rings, or should ring. I don't know if they're going to get the bells ringing or not this semester, but right at 2 o'clock we'll start the quiz, so make sure you're here on time. The quizzes are designed to be completed within 5 minutes, so if you're late, then you are eating into the time that you have to take the quiz. So class time is very precious, so we need to make sure that we're here right on time. The quiz will only cover material that we've already covered in class. So today, we're going to get very close to finishing chapter 1. We'll have a little bit of stuff to wrap up on chapter 1 before we start chapter 2 on Friday. So the quiz on Friday will cover everything through what we get to through the end of class today, which will be the connection between electronegativity and polarity. Okay? And the quiz questions are designed to be of comparable difficulty to the homework problems that are within the chapter. I've told you that there are the two types of homework problems, the ones that are within the chapter and the ones that are at the end of each chapter. The ones that are within the chapter are generally the easier level questions, the ones that are basically designed to test your understanding, your basic comprehension of the concepts rather than to apply them to challenging problems. So if you have been reading the book, taking good notes, paying attention in class, and working those assigned problems within the chapter, then you should be well prepared for the quiz. Okay? Again, designed to be completed within 5 minutes, so usually there's only like 2 or 3 very short questions for you to answer, usually in a short answer format. Okay? Any questions? All right, so on Friday, we were discussing bonding. We talked about molecular orbital theory a little bit. We talked about valence bond theory. We talked about the connection between surfing and chemistry, which is something I'm a big fan of. Today, we're going to continue our discussion of molecular orbital theory. Then we're going to go back and discuss an aspect of valence bond theory, which is hybridization, something you should be familiar with. And then we will discuss the connection between bond length and bond strength, and we'll conclude with a discussion of electronegativity and bond polarity. Okay? So I've drawn for you here what we ended with on Friday, which was the molecular orbital picture of the hydrogen molecule. We said that molecular orbitals are formed by combining atomic orbitals. And we said that the number of molecular orbitals in a molecule will equal the number of atomic orbitals that were used or that were present in the individual atoms that were used to be combined to make those molecular orbitals. So in H2, we have a 1s atomic orbital on each hydrogen. Therefore, we would end up with 2 molecular orbitals. We added those atomic orbitals together to generate the sigma orbital, which is known as a bonding molecular orbital. It looks suspiciously like the sigma bond that we get from valence bond theory by overlapping our 2 1s orbitals, and it is the same thing. But then we had to subtract. That was our other way of combining our atomic orbitals. We invert the sign of one of those 1s orbitals. We overlap them, and what we end up with is something like this. We get a node in the middle where these 2 orbitals overlap each other. They cancel each other out. And so we get a node in the middle where the probability of finding the electrons is 0. And the electrons in this orbital would be primarily outside of these atoms as opposed to being in between both nuclei. So as you might imagine, if you put electrons in this orbital, they would not contribute to the bonding at all because they wouldn't be in between the nuclei. Therefore, this is referred to as an anti-bonding molecular orbital, or a sigma star orbital. Okay? We'll come back to this in a moment, but first, let's draw an energy diagram. Each of these orbitals has an energy level, and we have our atomic orbitals, our 1s atomic orbital from one of our hydrogens. It has one electron in it, in just a hydrogen atom. We have the 1s atomic orbital of the other hydrogen. And when we combine them, a key principle to remember in molecular orbitals is that the sums of the energies of the molecular orbitals must equal the sums of the energies of the atomic orbitals that were combined to create them. So we have a sigma molecular orbital down here. That's going to be lower in energy than our 1s orbitals. And then we have our sigma star molecular orbital up here that is higher in energy than our 1s atomic orbitals by the same magnitude as the sigma, or the bonding molecular orbital, is lower. Okay? And so, because electrons in molecules are going to populate the lower energy orbitals first, we see that in H2, our sigma molecular orbital will be filled, and our sigma star, or antibonding molecular orbital, will be empty. Okay? So this aspect of molecular orbital theory fits nicely with what I told you last week about bonding. I told you that bonding is a favorable process. Bonding lowers the energy of electrons, lowers the energy of molecules. And so you see that when we take two hydrogen atoms and join them together to form H2, we lower the energy. The electrons end up in a lower energy orbital. So that's good. And because the sums of the energies of the orbitals have to be equal, we have to have an empty orbital that is higher in energy by a corresponding amount. Okay? So you might be wondering, well, what's the significance of an empty orbital? Especially one that's called an antibonding orbital. Well, it becomes significant when we start talking about reactions. In reactions, bonds in our starting materials will break, and they will be replaced by new bonds that are formed in the products of a reaction. Okay? So if we were to have a hydrogen molecule react with another species, that species or molecule would collide with the hydrogen atom. And if it collided in such an orientation that a filled orbital in the reacting molecule overlapped with our empty antibonding molecular orbital in the hydrogen molecule, then that collision could contribute to breaking the HH bond. Okay? So that's where antibonding molecular orbitals become significant, is if you have collisions between two reactants, and those reactants collide in an orientation that allows a filled orbital in one molecule to overlap with an empty orbital in another molecule. That can trigger the bond breaking, and then also the new bond forming that would occur in that reaction. Okay, so that's pretty much all we're going to say on the subject for now. But that's what the significance of an empty orbital is. An empty antibonding orbital is something that when you're looking at a molecule that's not reacting, that's just sitting there, it's going to be empty. But when you have reactions occur, you can have electron density being transferred into that orbital from another reactant, and that triggers a bond breaking event. Any questions? Okay, so the chief difference, well, first of all, before I talk about the difference, I will say that of our two theories, we will spend much more time using the valence bond theory in this class than we will molecular orbital theory. Okay, my view on theories is the simpler the better. If you have two theories, one is simpler than the other, and they both give you the same explanation, my view is stick with the simple one. Keep it simple. Okay? So in most cases in this class, we're going to explain reactivity, and we're going to explain properties of molecules using valence bond theory. However, there are a few types of molecules and a few types of reactions that are explained better using molecular orbital theory. And so when we get to those, we'll use it. That will mostly be in 352M. Okay, so the second semester, we will do that primarily. So for now, we're just teaching you enough about molecular orbital theory so you'll understand the basics and you can kind of compare and contrast molecular orbital theory to valence bond theory. The chief difference between the two is that in valence bond theory, we are localizing the electrons to specific locations. The electrons are either going to be in bonds between two atoms, or they're going to be in lone pairs that are anchored to a single atom. Whereas in molecular orbital theory, we're saying that electrons can be delocalized and electrons can be spread out across an entire molecule. Of course, we know the latter is accurate. We know that electrons can be delocalized, but there is a way to account for delocalization of electrons using valence bond theory. What is it? Resonance, exactly. So when we're drawing resonance structures, that's how we are using valence bond theory to account for the fact that electrons can be delocalized. Okay? So we can account for electron delocalization using either theory. Okay? Any questions? Yes, please. And valence bond theory? Yeah, exactly. So the molecular orbital theory has the delocalization kind of built into it, whereas you have to kind of add on resonance structures to valence bond theory to account for electron delocalization. And molecular orbital theory involves a lot fancier math. I'm not much of a mathematician myself, or my field of research doesn't require a lot of math, so I haven't done math since I was your age, really. So we're not really going to get into molecular orbital theory that deeply because of that. Okay, so let's go back to valence bond theory. To set the stage for this discussion, let's look at the ground state electron configuration of carbon. We look at carbon, its position in the periodic table, and we're just looking at the valence electrons. It has 4 valence electrons, so your 2s orbital is going to be filled. 2px, 2py are each going to have 1 electron in them. Okay? So ground state carbon has 2 half-filled orbitals. Based on that, how many bonds would you expect carbon to form? It has those 2 half-filled orbitals, so it could form 2 bonds. Yes, but we know that carbon can form 4 bonds. That's not consistent with this picture. Who would like to raise their hand and explain to me how we can rationalize the fact that carbon forms 4 bonds? Yes, please. Okay, so you're saying that we can use hybridization, specifically sp3 hybridization, as a way of explaining how carbon can form 4 bonds. And that's exactly right. Okay, so who would like to raise their hand and explain what hybridization is? You did a decent job right there, but let's see if someone else wants to elaborate on that a little bit, explain what hybridization is. Don't everybody raise their hands at once. Let me ask another question then. What is a hybrid? You can raise their hand and tell me what a hybrid is. Yes, please. A mixture. Yeah, a hybrid is a mixture of things. So when we are performing hybridization, we are mixing things. And what we're mixing is atomic orbitals, and we're creating hybrid orbitals. So here's a figure. This figure is not in your textbook. It's from another textbook, but I think it does an excellent job of showing the hybridization process. All of the figures I show you on the screen are on Learning Suite, so you can go back and look at this figure even though it's not in your own textbook. So here we have the ground state configuration of carbon, what I drew for you on the board. The 2s orbital is filled, and 2 of the 3p orbitals are half filled, because we know that the Lower energy orbitals get filled first, okay? Now, my high school chemistry teacher taught me about hybridization, and she did it in a way that was more effective than I've heard anybody else do. And so her explanation has stuck with me to this day. So the way she explained hybridization is, she said, you take your atomic orbitals, your 4 atomic orbitals in this particular case, and you put them in an imaginary bag. And then you shake that bag up. And as you shake up that imaginary bag, you're mixing those 4 orbitals together. And then when you pull them out of the imaginary bag, you get 4 equivalent orbitals, okay? Because they've been mixed. In this case, we've mixed 1 s orbital and 3 p orbitals. So the hybrid orbitals we get are 1 part s and 3 part p. So that mixing process is just some sort of fancy mathematical process because these are all fancy mathematical equations. That's what an orbital is. That's how I defined it last week. And so the hybridization process, this imaginary bag, is just a mathematical mixing process. And what we get out are, in this case, 4 identical hybrid orbitals, referred to as sp3 hybrid orbitals. So there's a few points that we need to look at in regards to these hybrid orbitals. Much like in molecular orbital theory, when you're hybridizing atomic orbitals, the sums of the energies of your hybrid orbitals has to equal the sums of the energies of your atomic orbitals. And the energies of your hybrid orbitals have to be equivalent to each other because they are equivalent orbitals. So you can see that these orbitals have the same energy, and their energy is in between the energies of the orbitals that they were hybridized from, but closer in energy to the p orbitals because you had 3 p orbitals and 1 s orbital. Okay? Another thing that we notice is that we have 2 different lobes. We have a big lobe and a small lobe. So if we centered these orbitals at the origin of 3D space, each of them would have a big lobe sticking out on one side and a small lobe on the other side. We'll come back to the significance of that in a minute, but one thing that you would find if you did that, if we centered all of these hybrid orbitals on the same origin, you would find that those big lobes are pointing out to the vertices of a tetrahedron. That's why hybridization is so important and so useful, because it explains what we observe in nature. Namely, that when we have 4 groups attached to a carbon, we have tetrahedral geometry. So those large lobes are pointing out to the vertices of a tetrahedron. So the fact that we have a large lobe and a small lobe is very advantageous for bonding. Okay? Would anybody like to try to explain why that is the case? Why would it be helpful to have a large lobe on one side and a small lobe on the other side in order to form a bond? Yes, please. Yes, the signs are opposite. Okay. Okay. Mm-hmm. Okay. Very good. So what you're saying, to summarize, is that when you have a large lobe on one side, you have a lot more area for that orbital to overlap with an orbital from another atom. Right? We learned last Friday that you have to have overlap, constructive interference, or overlap between orbitals in order to form bonds. One bond is only going to be formed on one side of an atom. And so if you have a hybrid orbital with a very, very large lobe on one side and a small lobe on the other side, that gives it more area to overlap, as you noted. And the higher the degree of overlap between the orbitals, the stronger the bond. Okay? So hybrid orbitals have a very nice shape, a shape that is ideal for forming sigma bonds. Okay? So those are key features of hybridization, specifically in this case, sp3 hybridization. Those large lobes point out in space in a tetrahedral orientation, which is completely consistent with what we observe in nature. And the uneven size of those lobes allows for much stronger bond formation than if those lobes were equivalent in size. So let's take a look at another figure which shows how we can use hybridization to explain bonding in an individual molecule. This is methane, our simplest organic compound, CH4, the principal component of natural gas. And here we have the ball and stick model with the orbitals superimposed on it. We've only drawn the large orbitals of the sp3 hybrid orbitals because those are the ones that overlap. In order to avoid unnecessary clutter on our figures, it's fairly common to leave off the small lobe when we're drawing hybrid orbitals. With p orbitals, we have to draw both, but with hybrid orbitals, we can leave off the small one, okay? So what we see here is that the sigma bonds in methane, or CH4, are formed by overlap of an sp3 hybrid orbital on the carbon with a 1s orbital on a hydrogen, okay? And that overlap is in the region between those atoms, and that electron density is going to be located on the axis between the carbon and the hydrogen atom in question. So let's look at a slightly more complicated molecule, ethane, which is a minor component of natural gas, C2H6. So in ethane, we have our two carbons. We have a carbon-carbon bond that is formed by overlap of two sp3 hybrid orbitals. And then we have three other sp3 hybrid orbitals coming off of each carbon. And each of those is going to overlap with a spherical 1s orbital on a hydrogen. Okay. So this is the picture of bonding that we would have in ethane. And what we see about ethane that's different from methane is that we have different types of orbitals overlapping to form sigma bonds. So here, our carbon-hydrogen sigma bond is formed by overlap of an sp3 hybrid orbital on carbon and an s orbital, atomic orbital, on hydrogen. But then we have the carbon-carbon sigma bond, and that is formed by overlap of two sp3 orbitals, okay? So we can form sigma bonds by overlapping different types of orbitals. We can have two hybrid orbitals overlap. We can have a hybrid orbital and an s orbital overlap. We could even have two different types of hybrid orbitals overlap, okay? But that's the message that we get here from looking at ethane, is that we can have sigma bonds formed by different types of hybrid orbitals overlapping. Question?
I don't want to get us off track, but what happens when carbon forms a double bond with itself? What does that look like?
That is coming next. That's actually not getting us off track. That is our next topic. I will show you something else first before we get to that. So this is a handheld model of ethane, where each of our blue balls here is a hydrogen atom. Each of our sigma bonds is represented by one of these black sticks. And then these little black tetrahedrons here are the carbons. And you can see that we can rotate freely about our sigma bonds, okay? All right, so any questions about sp3 hybridization and tetrahedral geometry of carbons? Those two things are connected, also connected to four groups, right? If we have a carbon with four groups, we have tetrahedral geometry, we have sp3 hybridization because that explains the tetrahedral geometry. But if we have three groups attached to a carbon, what is the geometry at that carbon? Don't be shy. VSEPR theory says trigonal planar. Okay, so sp3 hybridization does not fit trigonal planar geometry. So we have to have a different type of hybridization to explain how we can have three different groups attached to a carbon. And what is that hybridization? sp2, exactly. So here's our figure that shows sp2 hybridization. It's the same process. We have our imaginary bag. We put our atomic orbitals into our imaginary bag and we shake them up. The difference is we leave out one of those atomic orbitals. We leave out one of the p orbitals. So we're only sticking 2 p orbitals and 1 s orbital into our imaginary bag. So we're going to get 3 hybrid orbitals out, and we call them sp2 because they're 1 part s and 2 parts p. Are they going to be higher in energy or lower in energy than the sp3 hybrid orbitals? Lower. Why? Yes, Minnie? Right, because we left out one of the high energy orbitals when we mixed them. They have a higher proportion of the lower energy s orbital, so they're still in between s and p, but they're a little closer to s. They're still closer to p, but they're closer to s than the sp3 was. Okay, very good. So these hybrid orbitals look suspiciously similar in shape to the sp3 hybrid orbitals. They have a large lobe and a small lobe. And so again, that's ideal for forming sigma bonds. A key difference is that, so they've kind of twisted on the side a little bit so you can see, you can't really see it as well from this figure. But if you were to put all 3 of those orbitals on the origin in 3D space, you'd find out that the large lobes point out in the trigonal planar geometry. So in the same way that sp3 hybridization does an excellent job of explaining tetrahedral geometry, sp2 hybridization does an excellent job of explaining trigonal planar geometry. Okay? Now, you'll see that we've drawn each of these orbitals as being singly occupied. You'll note that this one is higher in energy than these 3, but they're close enough that if we're just looking at an sp2 hybridized carbon, we would say that it has these 4 electrons available in those orbitals for bonding. Okay? So let's take a look at a molecule that has sp2 hybridization and see how we can use that sp2 hybridization to explain the bonding and the shape of the molecule and the geometry at the carbons. So this is ethylene C2H4. We mentioned it last week as well. It is one of the most important chemicals industrially in the world, and it also is a hormone released by plants that signals that it's time for the fruit to ripen. So what this figure here on the left shows the sigma bond framework in ethylene, where we have a carbon-carbon sigma bond formed by overlapping 2 of those sp2 hybrid orbitals. We have carbon-hydrogen sigma bonds formed by overlapping other sp2 hybrid orbitals with the 1s orbitals on hydrogen. And then that leaves us with a p orbital on each of those carbons. So we would have a singly occupied p orbital on each carbon. Now, if those p orbitals are lined up with each other, if they're coplanar with each other, parallel with each other, they can overlap not in an end-on-end fashion, like when we form a sigma bond, but in a side-on fashion, side-to-side fashion, to form what is known as a pi bond. Okay? So end-to-end overlap makes a sigma bond, and that gives you the electron density on the axis between the 2 atoms. But side-to-side overlap gives you a pi bond, and it gives you a bond in which the electron density is going to be above and below, but not in the plane that those atoms are involved in. Okay? So overlapping our p orbitals gives us the pi bond. So the double bond, to answer your question, a carbon-carbon double bond then has 2 components, a sigma bond formed by end-to-end overlap of sp2 hybrid orbitals, and a pi bond formed by side-on overlap of the p orbitals. Okay? And here is my handheld model of ethylene. So again, we have our sigma bonds represented by these black sticks. The p orbitals, in this case, represented by these blue sticks. And then I've used these rubber bands to show the overlap of those orbitals and the pi bond. I chose the rubber bands because what would happen if I were to twist about the carbon-carbon bonds of ethylene? What would happen to my rubber bands? They would break. I don't want to hit myself in the face, so I'm not going to do it, but they would break. And so that's important because if we were to twist about the carbon-carbon bond in ethylene, we would break the pi bond. If we twisted here, these p orbitals would not be able to overlap, so we would have no pi bond. Okay? Now that pi bond is strong enough that there's not enough energy available for us to heat up an ethylene molecule and cause that pi bond to break. Okay? So not only is ethylene a planar molecule, but you cannot rotate about the carbon-carbon bond of ethylene, unlike the free rotation that we have about the carbon-carbon bond of ethane. Okay? And that's a consequence of forming the pi bond. Question? The importance would be, it's important for us to know what molecules are capable of doing in three-dimensional space in order to understand their properties. And so knowing that some molecules can rotate and others can't will help us understand differences in their properties. Okay? All right. Any questions about sp2 hybridization? Yes? The pi bond is made up of 2 electrons, yes. Yes. That's a bit of an oversimplification. I would just say that those 2 electrons are constantly in motion, moving back and forth from one side to the other without ever being in the plane. How it does that is fancy physical chemistry that we're not going to get into. But just recognize that you have 2 electrons in a pi bond, electron density above and below the plane, but not within the plane. That's as deep as we're going to go. Okay. We also know that carbon can have 2 groups attached to it. And what's the geometry when we have 2 groups attached? By VSEPR theory? Linear. Okay, so we're going to have linear geometry with 2 groups. And so that cannot be explained by sp2 hybridization or sp3 hybridization. So we need another type of hybridization. What is it? sp. Okay. So here's our figure for sp hybridization. In this case, we leave out 2 of our p orbitals. So we're only putting one of our s orbital and one of our p orbitals into our imaginary bag when we do our hybridization. And so when we get out our 2 hybrid orbitals and 2 unhybridized p orbitals. So our hybrid orbitals are 50% s, 50% p. So they're exactly halfway between our s and our p orbitals. Again, you see we end up with a similar shape. Large lobe on one side, small lobe on the other side. Ideal for forming sigma bonds. And then we have these p orbitals, and the unhybridized p orbitals are perpendicular or orthogonal to each other, okay? Kind of forming a cross. And that'll be important in a moment for us, okay? Any questions on how we generated our sp hybrid orbitals? All right, so here's the figure of our simple molecule with sp hybridization, acetylene, C2H2. It's a gas that's used in the welding process. It burns very, very hot. So that's what makes it useful in welding. It burns hot enough to be able to melt metal so you can stick them together. That's what you do when you weld. What we're most concerned with right now is the molecular structure of acetylene. And each carbon has 2 groups attached, so we use sp hybridization to explain that geometry. The sigma bond framework is formed by overlap of those sp hybrid orbitals with another sp hybrid orbital in the case of the carbon-carbon bond, and with a 1s orbital on the hydrogen in the case of the carbon-hydrogen bonds. This leaves us with 2 p orbitals on each carbon, and we can overlap each of those p orbitals with a p orbital on the other carbon, forming 2 pi bonds. So that's how we end up with a triple bond. A triple bond is comprised of 1 sigma bond and 2 pi bonds. And so we see that over here. This is 1 sigma bond because the different colors is showing you the different signs of those wave functions, right? Red is one sign. Blue is, we'll say blue is positive and red is negative. But it doesn't really matter. This is 1 hybrid orbital, or one pi bond, and this is the other pi bond. Okay? So The sp hybridization explains very nicely our linear geometry. Here is our model of acetylene. Here we've used these red sticks to represent one of our pi bonds and the green sticks to represent another pi bond. You can see that those pi electrons do not overlap with the pi electrons in the other pi bond, which is important because if they did, they'd repel each other. That would be destabilizing. So it's important to have those two pi bonds orthogonal or perpendicular to each other. Any questions? Okay, so it's very important to connect three concepts: the number of groups attached to each atom, the geometry of that atom, and the hybridization of that atom. Those three properties are all connected. And notice I said atom. We've talked about carbons being hybridized here, but it's not just carbon. We can have other atoms. Nitrogen, oxygen can also be hybridized as well. Okay? Any questions? All right, so let's practice this concept. It's time to get out your iClickers. And what we have here is actually 3 iClicker questions embedded in one slide. Occasionally we'll do this. We'll have more than one question on a slide. We have a molecule here. We have 3 of the atoms labeled, these 2 carbons and this oxygen, and we have 4 choices. So we're going to go ahead and talk to our neighbors, and we're going to determine the hybridization of each of these atoms, but we're going to answer the questions sequentially. So I'm going to go ahead and click this green arrow and open it up and make sure that your clickers are set to the CD frequency. And right now you're answering number 1. So what is the hybridization of this carbon labeled as carbon number 1? We'll give you about a minute and a half or 2 minutes. Go ahead and talk to your neighbors if you need to come up with the answer to question number 1 only. Okay, looks like we're pretty close to having our answers. Looks like there's a couple of you, if I've counted correctly, that still haven't answered. So we'll give you about 10 or 15 more seconds. Let's come up with our final answers. See if we've got any more that need to come in here. Okay, any more answers? If you get the green light or I think it's a green light, you know that you've answered correctly, or your answer has been recorded. All right, looks like that's all we have then. Going once, going twice. So what I'm going to do now is I'm going to close question number 1. I'm going to open question number 2. So now you're going to answer the hybridization of atom number 2 here. You can still talk to your neighbors. You guys are a lot quieter than the 1 o'clock group. I know there's less of you, but still a much quieter group. I don't know if that's good or bad, but it's just an observation. Okay, we'll probably take about 10 more seconds or so. Based on the number of answers we had to the last one, we should get to 18. So we just made it to 18. We'll give you another few seconds if you want to change. Oh, we have 19. We have one that didn't answer the first question. Okay. All right. Going once, going twice. All right, so we'll go ahead and close number 2. And now we've opened up question number 3. What is the hybridization of atom number 3? Based on the responses I'm getting, there's a little more debate on this subject than there were on the first 2. So we'll give you a little time to discuss that. All right. Oh, we got to 20. We have one more answer on each of the last 2 questions. That's unusual. But anyway, we'll give you 5 or 10 more seconds to finish it off. We made it to 21. All right. Going once, going twice. All right. We'll go ahead and close that. So, number 1, what's the hybridization? sp3, 4 groups equals sp3 hybridization. Number 2, what's the hybridization? sp2, 3 groups. sp2, what's the geometry then at this carbon? Trigonal planar. So that tells us that we have 3 sigma bonds to this carbon, and then we have an empty p orbital. That's something we'll come back to later in the class when we learn more about carbocations. Question? This particular molecule would be high in energy, yes. This is not something that you could store on a shelf. It's the sort of thing that does exist. You could make it, but it would then react pretty quickly. So it's known as a reactive intermediate, something we'll talk about in more detail in chapter 6. Question? Nope. Nope, this just has 2 carbon-carbon bonds, 1 carbon-hydrogen bond, and an empty orbital, because we learned last week that a positive or a negative charge replaces one of the valences. So you have this one here and that one there. Yeah, this hydrogen is not, so this is the skeletal formulas. Okay, very good. All right, the third one. There was some debate here, so I'll just ask a question. I'll ask a couple leading questions. How many groups around this oxygen? 4. What's the geometry? Tetrahedral. So what's the hybridization? sp3. This is sp3 hybridized because it has tetrahedral geometry. Okay? And so what we learned from this example is that hybrid orbitals can contain lone pairs. In this case, we have 4 sp3 hybrid orbitals on that oxygen. 2 of them are used to form carbon-oxygen sigma bonds. 2 of them contain lone pairs. Any questions? All right, so we have a summary table. These summary tables do a great job in our book of summarizing topics, and we don't want to memorize the information in them. We want to make sure we understand the information in these tables. Okay? But let's move on now to another table. This table is examining the connection between bond length and bond strength. We've already learned that shorter bonds are stronger bonds. So here in the top of the table, the top half, we're comparing bond lengths of carbon-carbon single, double, and triple bonds. We would expect triple bonds to be the strongest, followed by double bonds, followed by single bonds. So the trend in bond length makes sense. the trends in bond strength make sense, okay? But if you look at these bond strength values and you compare them to each other, something should jump out at you. What do you notice when you look at these values and you compare them to each other? Yes, please. Just the units. Kilocalories is not in parentheses. Kilojoules is in parentheses. Organic chemists like to use kilocalories. So we like these. We're not like the rest of the chemists that like kilojoules. Okay? But regardless of the units, if you take either of these and you compare them, compare this number to that number, you'll notice something. Yes? Okay? It almost doubles, but not quite. Right? And then you see a smaller increase in bond strength when we go from the double to the triple bond. So that tells us something important. It tells us that pi bonds are weaker than sigma bonds. Okay? So that's the message of the top half of the table. Pi bonds are weaker than sigma bonds. That's important because when we talk about reactions, I've already told you that in reactions, bonds break. They're replaced by new bonds. And so if we have a molecule that has pi bonds and sigma bonds, it's more likely to have the pi bonds break in a reaction than having the sigma bonds break. We'll see that when we get to reactions later on. All right, down here, this is a little bit different. We're actually comparing carbon-hydrogen bonds, 3 different carbon-hydrogen bonds, the one in ethane to the one in ethylene to the one in acetylene. And we see there's a small but measurable difference in bond length, which is connected to a measurable difference in bond strength. We're saying the carbon-hydrogen bond in acetylene is stronger than the carbon-hydrogen bond in ethylene, which in turn is stronger than the carbon-hydrogen bond in ethane. Why? Who would like to tell us why? What's the difference, first of all? Yes? Okay? Okay? What kind of hybridization do we have on a carbon that forms a triple bond? sp. What kind of hybridization do we have on a carbon that forms a double bond? sp2, and then we have sp3 here. So that's the key difference that we have, is what we would call the percent S character of those hybrid orbitals involved in forming the carbon-hydrogen sigma bonds. sp3, we would say, has 25% S character, because it's 1 part S, 3 parts P. sp2, 33%, sp, 50%. Okay? So, which atomic orbital is closer to the nucleus, S or P? S. Okay? So if you have a higher percent S character on a hybrid orbital, that orbital should be closer to the nucleus. If you have electrons in a hybrid orbital closer to the nucleus, they're attracted more strongly to that nucleus, giving you a shorter bond that is a stronger bond. So that's what's going on here. So the message from the bottom half of this table is that when you have a higher percent S character in your hybrid orbitals, you're going to form slightly shorter and stronger bonds. Any questions? All right, let's now talk about the connection between electronegativity and polarity. Electronegativity, a measure of how strongly an atom attracts electrons. What happens to electronegativity as we go across the periodic table? Increase or decrease? Increase, right? We're adding protons, we're adding electrons, so we have a stronger attractive force. Okay? What happens to electronegativity as we go down the periodic table? Decreases, right? We're adding energy levels. Those outer electrons are further away from the nucleus. They're not attracted as strongly. So you understand the trends. Now, we have 2 types of bonds, 2 types of covalent bonds in organic chemistry. We have nonpolar. Nonpolar bonds are formed between atoms of equal or almost equal electronegativity. In organic chemistry, those will be our carbon-carbon and our carbon-hydrogen bonds. Polar bonds are formed between atoms of sufficiently different electronegativity. Your book says 0.5. We're not really going to worry about numbers here. We're just going to recognize that in organic chemistry, these are our nonpolar bonds because carbon and hydrogen have very similar electronegativities. And all the rest, carbon-oxygen, carbon-nitrogen, CX means carbon-halogen, all these other types of bonds to carbon and other atoms than hydrogen or itself will be polar because of electronegativity differences between carbon and those atoms. So when we have a polar bond, we have what is known as a dipole or a separation of charge. Okay? And there's two ways to show that. If we have a carbon-oxygen bond, right, we'll have three other groups bonded to that carbon, one other bond to that oxygen. Oxygen is more electronegative than carbon, so we can draw a vector pointing from the carbon to the oxygen, indicating that there's more electron density on the oxygen than the carbon. Because that oxygen is more electronegative, it's pulling on the electrons in this sigma bond more strongly than carbon is. We can also represent that in another fashion. We can write a partial positive charge on the carbon, and we can write a partial negative charge on the oxygen. So two ways to show this dipole or this polar bond. Last thing I'll show you is an electrostatic potential plot. This is the third way of showing polar bonds and dipoles in molecules. And it's very easy for BYU students to understand this topic. So what we do is we use blue to represent regions of low electron density or partial positive charge. So blue represents positive. We use red to represent regions of high electron density or partial negative charge. So blue is positive, red is negative. What could be easier to understand, right? And you also see our other two methods shown over here with this particular molecule. You see our vector and you see the partial charges. Any questions? All right, we'll have our quiz at the beginning of class on Friday. We've got one or two things to wrap up in chapter 1, and then we'll jump into chapter 2, acid-base chemistry. See you on